Morning, everyone. So we continue with our Lefschetz marathon. So it's an immense pleasure to introduce myself as writer from Donagi. We're going to tell us about the intersection of the quadrics in this. Thank you.
Thank you, man. Thank you, everybody, for the invitation. We're not being here in Miami. Can people hear me okay? That's okay. That'd be good. Thank you. Just to set things up, a variety X is said to be rational if it's birational equivalent to projected state. You look at the rational map from N to X. So it's unirational, the dominant rational map and could be bigger than the dimension of X. In other words, if you can parameterize, multi-parameterize X by that's a parameter, then you say that it's unirational. And classical problem algebraic geometry was where they have a irrational variety. That's rational. So Lord showed in the 19th century that the answer is yes in dimension 1 is modern terminology is essentially triviality for in rock. Similarly, the classification of surfaces said that the answer is yes in dimension 2. Every surface that's dominated by a rational variety is rational. In 1972, we learned that the answer is negative in dimension 3. So Clemens and Griffiths, watching in the audience, introduced the intermediate covariance variety, which showed that it gives an invariant of the rational equivalence. And they use that to show the cubic threefold is irrational but not rational. It's been known to be irrational. In the same year, Tony Pantev showed that the torsion H of X3 is also invariant. That?
Yeah, I'm going to put it here.
Better now? It works? Better, thank you.
Thank you.
So the example that I've been considering was the double cover of P3. We take a web project that we take the linear system of quadrics in P3, that's P9, take a generic P3 in there. It comes with a double cover, which each point you assign the two rulings of that quadric. And we show that variety, double cover P3 that you get this way, is again irrational but not rational. And shortly thereafter, it's called C9 and show yet a different technique, namely rational orthogonal groups, to show that some quadrics for the creation of threefold are also rational. A lot of other work is gone by, a lot of other examples are known. But as we heard already on Tuesday, the KKPY plot program, that was percentage planted a year, shows that the general control for the reaction but not rational. It also shows a certain families control. Trying to a family is harder than trying to for the whole thing because maybe that family is exactly the exceptional one. So in this talk, we're going to consider X, which is very general smooth, complete intersection of three quadrics etc. We get 4 dimensions. Natural associated to it is a surface S, the geograph on S, I'll describe that momentarily. And it's basically what I just said in the argument, for example. We take the net quadrics, and to each of these quadrics, we assign 2 things, 2 rulings on it, then double couple into that surface S. We'll describe the geograph in a minute. Look at the graph category for the pair S alpha. And it's known as the summand of the dark category of X. By studying the shift theory of the germ, we show that the natural non-commutative space attached to X is truly non-commutative. So that's the emphasis on the word truly. I try to illustrate what that means. In particular, it's associated with K lattice and lattice more K lattice any small projective surface. So the relevant derived category is not equivalent to the derived category of any small projective surface. So I'm going to say a few very general words and the rest of the talk will be very concrete, down to earth, classical algebraic geometry type calculation. So using the new theory of Hodge, I can prove the irrationality of the very general intersection of the quadrics. This result was retrieved with very different methods by Hasselhoff and Chick. So here's some of the general comments. First, what is GMs and germs, which I'll describe in a minute, are very interesting for a variety of reasons. For example, they contain essential information about the complexity of the vowel classes, it's sort of the common playground for geometrical constructions, for presentations, and most pertinently for us, provides standard examples of non-commutative space. So in this non-categorical approach to non-commutative algebraic geometry, which is Tony Pantev, wlll, so on, when studies co-complete triangulated ciliary algebraic categories, that's better. These categories are viewed as leaky versions of the categories of quasi-clear machines on those putative non-commutative spaces. And so in general, we don't have a description of those spaces. Those categories are actually taken to be the geometric object themselves. The categorical point of view towards NC geometry allows for unified treatment with complex and symplectic manifolds as well as quantized and static geometries. So a lot of things fit together. Geometric properties such as being algebraic, being smooth, proper, collabial, those notions are intrinsic to the NC space. They can be described without actually saying what the underlying geometry is. Or in situations where there is no geometry underlying. More with homological to the smooth proper NC space, and hence additional algebraic structure, namely the data comprising a pure non-commutative block structure. Classical algebraic geometry fits within this formula, of course, because a classical scheme or an algebraic stack can be regarded as a non-commutative space for which the corresponding category is really a digit enhancement of the cross-covariant category of Y. There are many other examples of NC spaces coming from geometry and physics. That include things like categories, symplectic manifolds, matrix related categories, right-sided categories for potential, and categories of boundary conditions, and just symmetry. The properties and structure of a non-commutative space correspond to open triangulated linear categories are captured in the subcategory of perfect object. Or a classical separated scheme, this notation is consistent with the standard notation. In other words, the perfect category is the category of objects which are locally present both defined and perfect. Among all the non-commutative spaces, there's an important class, the ones of geometric origin. That means they can be embedded into the direct category or into proof of some scheme Y. And some of the key examples of those are component defined manifolds, residual categories of spherical factors, and direct categories of twisted shears and source projective variety. And I'm going to focus on the last one. These examples of special interest, they're expected to give new variation in variance of source projective variety. And in particular, it's expected that for truly non-commutative NC spaces of geometric origin will be variation and variance in projective variety, for which they are realized geometrically. Well, general limits of components in the categories are frequently distinguished from symplectic variety by standard Hodge theory invariance. This is less common when you're talking about NC spaces. So to illustrate the confusion of the difficulties here, let me remind you that if you have any sort of predicted variety X, so we call this number, and then the unknown effect brow plus alpha, that gives us a DG category dB of X twisted by alpha. So the object of alpha twisted we can choose, or alpha twisted to the complexes. One, if you prefer to think of this derivative as my algebras, the brow plus alpha corresponds to some as my algebra over X, and this is the theory of A mod for A density as my algebra. And then this category embedded in this subcategory is the Gauss variety of alpha, which is projected space bundle over X. So it corresponds to an non-commutative space, let's call it sub alpha X, putting the alpha on the left. There is some geometric origin, but unfortunately, what you want, interestingly, it can happen that this non-commutative space alpha X is secretly commutative, even in the brow class alpha X is non-zero. And indeed, suppose X is smooth projected surface equivalent to the Lefschetz configuration. So X, if you want, is a section sigma. Then, in this case, when the brow group can be identified to the algebraic group sharp X, and this correspondence is very geometric. In other words, each element alpha in the algebraic group, by definition, that's realized by its smooth projected K3 surface X alpha, which is part of the genus 1 curves or Q1, but no section. So the trivial object is the one that has a section. The others have genus 1 derivation and then elliptic, the relative Jacobian K3X, with a different K3 surfaces. So, but there is a great sheet from the power part about alpha X and X alpha. That is an equivalent of categories between dB X alpha and dB X alpha. So the non-commutative space alpha X is secretly isomorphic to the classical K3 surface of alpha. So it's not truly non-commutative. This phenomenon shows the question of recognizing whether a non-commutative space corresponds to category to achieves to a non-commutative is quite subtle. There is a method for distinguishing such NC spaces from commutative ones. It was proposed by Kuznetsov. It boils down to checking, it boils down to its K theory, its K lattice. And basically you check whether there is an object in there that could play the role of a point. If there isn't an object that has the regular invariance that the point should have, then the thing cannot come from geometry. Kuznetsov is trying to show the kind of twisted shapes associated with a very general four-dimensional cubic. It contains a plane that's really not commutative. And in this talk, we use Kuznetsov method to show that the natural NC space attached to an intersection to quadrics 57 is also truly non-commutative. More precisely, when X is a general non-commutative intersection of the quadrics, the direct category of X has a semi-orthogonal composition with a couple of exceptional summands, and the main one is this dBx alpha. Whereas the subs of general type, which is not coupled with plane, as I described before, it's branching on a smooth optic curve, and alpha is a two-tone brow cloudiness. So the study the direct category of S alpha tells us it's about the direct category of X. So what we do is we look at this lattice lambda when we spread it out. So alpha is nature S of star, that's the brow class. We assume that it's of order 2, that means there's a B in H2 of the S with half the same coefficients that exponentiates to alpha. So then we take the lattice HSBC to be the Hodge classes twisted by the exponential of this B. Basically twisted by alpha. And there is more calculated, which I will remind you of in a minute. And we get this lattice that carries all the relevant information. After isomorphism, the lattice depends on an S and alpha, not in B. And we show that lambda cannot be isomorphic in high level than into Hodge classes. The consequence is defined given that X be a very general intersection of the three quadrics in B7. That is often be the associated source of general type in the ground group. The associated numerical K lattice is not isomorphic to the lattice of any so this, and in particular, BBS alpha cannot be equivalent to the direct category of any such surface. And this has, using the KKPY work, this implies the coordinate that the very general intersection of the quadrics in B7 is not rational. Okay, so now we set all the generalities aside, and let's just do some ordinary classical geometry. So we start with P7. We look at the space-ball quadrics in P7. We look at the net. So A is generic, P2 inside is P. So basically, it's you're taking three independent quadrics and taking only the combination of those quadrics. Let X be the intersection of those quadrics. That's the 4-4 cube in P7. We're assuming A is sufficient general, so the singular quadrics in the net on the correct one. No more degeneration than this. The Schumann curve is going to be a smooth curve 3 just given by the determinant of the radius of quadrics. In B7, so it's an A determinants of optic. We did the section X always contains lines. So if you both with the top, you might want to play around with this. Convince yourself that for every point that's in the section, there is a line. In fact, the whole problem is calculate how many lines there are per generic point. It's specific finite number, simply finite. Anyway, that proves that X is universal. We have a point there is a line that, and the element of this line is up the interaction surface. So, well, I just should it's a new rule and it's a little more what you say this interaction. So we fix once about one line, and the entire story is going to depend on this one line we fix. And we take the line to be general enough so it does not intersect any of the vertices dependent on the simplifier. Can you have me? So in a minute, we're going to look at this variety Y, the length of this variety. So the resides I will do all the different pages. I will just slide up and down. The rest you have here.
Yeah.
Yeah. We're looking at a set of pairs. Remember, L is fixed. L is one fixed line with segment 4. We're looking at the plane pi, which is contained one of the quadrics. Contain this. This is contained part of the A cross line. Because one and quadrics with planes in P7. The A quadrics the quadrics. So this Y always the 5 over A plus projection. That's 5 over this line. The general point T in A, as well as the quadratic, determines 3 things. There's a capital piece of T. It's going to be a 5-dimensional projected surface. Namely, so I'm in P7, I have a line. And I have a quadratic containing that line. Each point of the line I can take a tangent type of plane. So dimension 1. The move along the line is happening from tensor. So the intersection is relation to the linear P5, which depends on the quadrant. Once P5 is contained, this common line there, I can uniformly divide on the way. So we can divide them, the 5 space becomes a 3 space. So the second object is little piece of T, which is a P3. So capital P is the sum, little p is the subportion. Inside capital P, if you look in the intersection raised by the QT, this is going to be a while the singular along the formal way, so I can divide by because the multiplied by little QT and P. So this is the main thing that I'm going to be working with. Where we put T in the main net, and now have a two-dimensional space with T and a quantum surface here. This is right to Y, that was over A as I said, and if I look at general T and A is a moving factor in this quadratic surface. In fact, there's birational isomorphism between Y and X. So in one direction, starting with pair T I, the intersection of the plane is a quadratic. Depends on the image, it's probably a similar quotient line being divided by T. This intersection is a pair line, and there's a fixed line. And one other line, let's call it the L subway, it's bar. That depends on the image is bar. So the line that is bar, that's bar and the way with T. Or a pencil line in the plane, they're in the intersection point, or the point A. So define now little a, the size of a pair, which is going to y, given by x. I can go backwards. Then this A is going to be in respect to the pair of pi, or pi, which is the span, the L and the point x. That's a plane. And T is going to be the unique value such that the quadratic community contains pi. Generate the assumptions on the net A and on the line L and it implies that Y is actually smooth and that the student curve for the family Y to A, the family quadratic surfaces, is the same as the student curve for the original family after Q, circulation lines. In other words, we start with Q to the net L, or smooth quadratic QT, because that little Q is also smooth. And conversely, it's after Q is singular, the fact that L does not meet the vertex. It forms me to the quadratic QT is singular with the same singularity. Because same chloride. Just terminology, the family of two-dimensional quadratics Y over A is called the hyperbolic reduction of the family of two-dimensional quadratics with respect to the line L. Families related by hyperbolic reduction are known to show many invariants in particular. So she showed that the discriminants are in general isomorphic, which we just saw explicitly in alchemy. That they have common pieces in automatic position in the draft pattern. Not that I'll generate the assumption. Total space Q of the standards dimensional quadratics is divided by degree 1, 2, and equal to 7. Because given by a matrix, which is linearity in A and quadratic in 7. So we can think of this as parameter by estimated matrix and parameter by A. Then it has linear forms on A. And that's why matrix should proceed with discriminants and optics, just given by the determinant of the same by matrix. Which is good thing. So next, I want to try to recover the same result, the fact that the discriminant is degrade by working with the little quadrics. Okay, the little people. So that does confusing, but you think that there's a family of quite sources in B3. expecting this range to just be able to be fully right in 8. So I think it's going to be able to be 4. But it isn't because they're not quadrics in a fixed projective space, they're quadrics in a bundle of projective space. That changes everything. So let me explain that. We found a three-dimensional projective space in the projectization rank 4 vector bundle E on A. And now y is going to divide over on the projectization that E. The linear system 1, 2. Where we want is the right bundle. One will describe that the fact that image is the dual. These terms family of two-dimensional quadrics. The two-dimensional map between bundle or 1. So what's the discriminant code? It's a section in OA is 4, the 4 means and only 20 minus 2. So that says the discriminant of A with the B, that will be OK minus 2. The term we cover it on way 3 works. That down. So remember that we're seeing this in the one specific. This E is not to the other by its own minus 2. Remember, if you take a general line in A, restrict and bundle E to it. Now it's vector bundle back forward the line. Because every vector bundle on the P1 splits the sum of line bundle. The same as the reason going to be minus 1, 0, and 0. Let's introduce a vector, dimensional vector space V, which position P7. Two-dimensional subspace after L, which position is L. The very symmetric matrix signal presenting A by definition matches on L. So that means we take the first 2 coordinates correspond to L, the other 6 coordinates to the equations of L. Then the upper left to go to corner of this matrix is going to have to be identity 0. And the lower left to by 6 block is the equation of the files. Inside the 6-dimensional vector space in model. In other words, I'm saying if you get a short by sequence, OA to the 6th, that means to log is OA 1 is identical. In particular, this confirm that the domain of the E isn't the way it should be in open lines. And the decision E to every line follows its initial the AI, some AI, so we know what the number is AI. Since we know this is some bundle of the third bundle, which follows that each of the AI is non-negative, non-positive. On the other hand, there's some minus 2. All of this is going to be either minus 2 and 3 zeros, or minus 1, which is 0. And then you just calculate the additional and the second one. This is the same by the number of sections. I'm sure that they will play that. We'll see. Let's see the additional 2 out of the 3, so it's anyway, let's focus now on the surface S. So it's a double cover of the net. Sometimes the rollers of the fibers of minus, so that's very few. But construction is a smooth surface, which is a double cover of the net, the optic curve. And the universal ruling of Y is as a P1 bundle, where it's such that powerful ruling. So when we're doing saying for each point of A, I have pocket points S. And each point S becomes the P1, which is the actual set of lines in that row. The P1 bundle over the double cover of A. So this R is about square variety. And the well plus alpha is just the class of this R and well. The definition alpha is a 2 ordinary in each And you can use the class of a sheet. What's my algebra that I had 4 breaths. Not going for every general choice of net. Or very generous choice of the net. The subset would be in the direction general. So you would have the algorithm. As most of the integers generated by the whatever. Okay, so let's take this generator for the H. Going back to section, it has some section 2. In the line has some section 1. Currently don't cover. Furthermore, S is the variable divisor in total space 44. So by the Lefschetz type section, dimension Lefschetz is 1 in every form. By the Lefschetz type section, for quasi-projective varieties, which will be similarly connected, so the figure H1 and H2 vanish. So therefore, we can use the exponential sequence to conclude that with the class beta in H2 of O, the exponential figure alpha, and it's not H2 so that is B in H2 of S having coefficients. So it's turning out half Z into Q into O that gives me alpha. So let's choose such class B. So it's a class in S solution having. It's not the multitude, it's having. This is the entire. The definition is alpha. Generally, class B itself is not unique. The different choice of B from a coset under some group. The integral classes or the happy one class. But nevertheless, the numerical invariants would be independent of these choices, and that's what we're very focused. So that raised the fraction product in our P is P minus its floor. It's easy to see that the fraction product within the section B was H. Then the choice would be. Indeed, we just check that if you change by anything that's allowed to change by a different class where I think you have a plus class, the fraction part will not change. But the value intersection will change by anything. In fact, this fraction part can be used in the geometry of the bundle of the broad square. So if the level of exposure all shows that CNS is kind of the linear system H, then the schema will know right. There's more fiction, utilization of some master and W on the curve. And the fraction part is the fraction part of half the degree of W. In other words, when we factor the fraction part of W by unprojected bias. The degree is even, fraction part is 0, the degree is odd, fraction part is half. So from this we deduce the following position, claim that the fraction part is actually a half. And for now, let's just say that fraction part of this choice is also independent of the choice. And we'll next one to get that in this. Let me just give you the idea of this. So again, B some line in the net. We take the general transversal to the arcade. Then it's pulled back. The smooth heaven to go to just terrain because it is H. Inside of this notation, that's still called projection part. So by definition, our frequency is the elliptic parameter line of the pocket continuing phase is taken to line. So let's just try to write E sub B and Y sub B for short. As before, we said that y should be the smooth threefold. It's fine with the quadratic surfaces, but now it's over the line. It's a smooth divisor over one to the relation of B within a system 2 over 1, thereby an exclusion section. And we work out what the E sub B is. So that's 2 copies of O and 2 plus 2 copies of O minus 1. So the trick is we're going to consider a subbundle F, which consists of 2 copies of the trivial and just 1 copy of the negative. So PB is a bundle of the phrase and in it is choose a subbundle of P2s. So in the sex YB, so YB with a quadratic surface, and then comes into the conic. So we got a bundle of conics. This is the best approximation of the Gothic thing, which fibers over the base is fiber the conic. So for general A and general B in it, the surface Gothic thing will be very smooth and all conics will be reduced. And in fact, this conic bundle is given by restricted time of the correct equation. So we had the equation sigma B for that, so that's just restricted U to F. The discriminant is a section of the determinant of F minus 2 to go over 3. The determinant of F is over minus 1, and this whole thing is over 5. So this 5 is the pivot point for the whole top. The point is that this 5 is an odd number. And that's going to tell us that the vector bundle will have odd degree. In the intersection of this will be a half integer. This is where we get the fact that something is not true. Again, we're taking DNA and general, we can distribute the family of conics, disjointed and discriminant the family of quadrics. So altogether we have 13 special points on this line. There are the 8 points where the line meets the octet. Those are the points where the quadratic circle drops in. There are 5 additional points where the conic drops in. And we're assuming those are disjointed. So we have a total of 15 points. And observe that each line of the quadratic circle intersects the conic with a single point. So for each thing, B is a good schema of T, we'll find the continuum described as follows. And I'm going to spare into detail. So you do a little bit of analysis. What does that line look like? And there are 3 cases to consider. The generic case, one of the 8 points, one of the 5. And the bottom line is to get the particular bundle of the signature to the hypothetical state. This is taken some protected bundle for performing 5 dimensional multiplication and the points and the 5 points for the rector. So this W is whatever it is. It's pulled back is when I get that bundle with even degree with putting that back double cover. So the degree here is even. We're doing 5 Hecke transforms, which then change the degree by 1, so that is odd degree. So the upshot is that the fraction point of the intersection of B with H is a half. Not. And then there's one calculation to check that the other number is also independent of the choice. So we let A and B very general quadrics in the clear sense. Let S be the double cover. Let H be the backup transformance. Then we go about calculations and here are some results. First of all, the subset is smooth, interconnected, with general type. This Chicago is going to be the integer generated by this hyperplane class H plus of 41. The product of 41 is actually the canonical class base. in the morphism pi, S is a plane, but we got it's given the complete linear system where S. So this is one way to see that S is general type. It's canonical image is related to the image. You can do the check classes, you find that C1 is minus H, while C2 is 46. So that's just a calculation. And from that, you conclude the Hodge diamond candidates. So all the interesting stuff is in the dimension. H0 is 3, H11 is 38. That's first add up to 46. Okay. So for this, I'm talking just going to tell you about the text. So you don't know how to get it. Those are one. Those give us the evidence that this category we're looking at does not come from geometry. So we're quoting Wigwert that if Z is a smooth complex project variety, that shows oil pairing on its K theory. Given this formula. So given an E and an F, we look at all the X between them, we take the alternating sum of the dimension for the pairing B and F. We also have the high vector map, which is multiplying by the square root of our class. This combined with it. If you combine this with what you can do here, allows us to express the order pairing in purely chronological terms. So the Mukai pairing itself, or the K theory, is given by first by the exponential of C1 over 2. We're going to point out that I have explained this being B prime. What I'm copying here is B prime is a dual of B, where the particular notion of duality simply says that you multiply the K component by square root of minus 1 to the K problem. Very happy. Even K, so this is plus minus 1. But when they come up, formula becomes simply that the pairing between E and F is the Mukai pairing. So the Fabian group, which is the image of the Mukai vector, together with the Mukai pairing, we call it the numerical K lattice, or the K numeracy. So remember I had this other lattice lambda, then define Hodge structure. This K node is going to be a sublattice lambda finite degree. Remember, when I'm going to worry about which subgroup it is, instead we'll just work with a larger thing lambda and show that it does not contain any classes could be the class component. Anyway, it's a small proportion of KZ by the kernel of the Euler pairing, and it's derived by the that was the straightforward version. There's an obvious twisted version. The final dot can go twisted sheet, which is variety. And the twist is given by a rational power class zeta, which is more of a topological trivial. Plus all everything will be topological trivial because H is 0. So the numerical K lattice can again describe so we're Donagi. Is the image in cohomology of the person who had vector map. It would present high pairing. And so what we're going to study this invariant for all particular geometry. Suppose that pi is not A don't have a branch to very general archaic. P be a class with a exponential component. And we're assuming that not dependent on the problem. Consider the boundary category of the first invariant sheets in this. Or as a rag model, So going parallel to that twisted case, we just twist everything. We have an alpha twisted order pairing, one of the alpha twisted case groups. It's given by same formula, something some dimension next time. And according to the Donagi, the choice of B as above gives what pretty good pairing in terms of the distance. More precisely, there exists a B twisted version of the Chern character, which is a new map your K group to the image of this twisted Chern character is defined in the symbol in the prevailing group. Essentially, that's what you have that. The alpha twisted order pairing is computed as before by this twisting will basically we are changing using the B twisted Chern character instead of the Chern character. After isomorphism, the pair consisting of the lattice and the pairing, it depends only on the alpha. But then this is how you build the cohort, the different lattice. So we call that K bloom as alpha, the word of K lattice, best first and back. And then the derived variant of the S alpha. So we need one that always said that it's not this is defined in some book in this particular area group. So look what they did. Actually, let's read the first couple of lines and then go back again. So a priori we have everything's rational coefficient is zeroish on one dimensional. But it's the Hodge class is considered. So and then the fact that R and DH at times point. So R again is a priori rational. Now if I X to that, you get some combination. And I want to work out the condition towards this person thing to be integral. So we learn using regulations, which I'm going to skip. And we just find that the coefficient R has to be the coefficient R in the gradient has to be even. So we have 2 plus 2b multiplied by something that is in this factor. Then the other coefficient has to be equal. Okay, so we know the Chern class of the surface is minus h. So the exponential is what it is, 1 minus half h plus quarter of a point. So if we have a class, 2 classes above in homology, then we can work out the different pairing. It is what it is. And we can now use this as a basis. We can write down the above h. Actually, what that explicitly with pairing is going to be a 3 basic values. Expressing pairing in terms of respective basis. And this is the measure that we get. So it's nice that we have a bunch of zeros that come here. We have 2s and 9s at end. So again, just relations with them. Skip to the next somebody really wants to see it. So the point is this now allows us to compute the fraction part of b squared, which is the average very unique. And the question could then against 3 pointers. I'm going to skip the description and just give the idea of how you do such a calculation. One is that you have a shape as my algebraics, is an image shown. And then Kuznetsov points out that the direct image of this is my algebra. So A is an algebra rank 4, the double couplet, so the direct image is rank 8. We look at that as the even part of the shape of algebra. So whenever we have a quadric, we have no common group, we write on a triple algebra. Triple algebra in this case will have a rank 16 to the 4. It breaks naturally into even and odd pieces. The even piece is rank 8. So identifies the even part of the triple algebra with A. Then the even part of the triple algebra in decomposes degree 0 piece, which is O, degree 2, degree 4. And those just recover the original left random. So you have all the moment and there's now this little bit of information which will escape. So that allows me to show the the classical point doesn't exist. I simply say, given these numbers, there are no elements beyond V2 with these properties. So I want V2 paired with V2 be 0, while V1 paired with V2 equals 1. Why is that what I want? Because if the given geometry, there will be the class with the surface, and the class with the point. The rank of the surface of the point should be 1, the rank of the point of the surface should be 0. So if the thing comes from geometry, there must be two classes that satisfy these properties. They don't exist. Right. So we just go to this overlap this lambda, and here are the two conditions we want to solve. V1 transpose GV2 is 1, V2 transpose GV2 is 0. V0 is that ground matrix. So write V2 as x minus z. This condition simply says, well, it's something. Let's reduce mod 4. 16 goes out. So when I reduce mod 4, I'm left with x squared minus 2x squared minus 2x squared. Now, notice that all terms here are even, except possible for the first term. We know about x squared. The thing is equal to 0 over 4, that x has to be even. But if x is even, no term is divisible by 4 except for the y squared. So y also has to be even. So both x and y have to be even. That says that the vector v2, where because of the matrix G and a bunch of zeros. In fact, the x and y are both even. That means that the intersection of v2 is v1 has to be even, so it can be 1. So that prediction. Putting all of this together, we get a result, which is that for the very general intersection of 7, the associated numerical K is not invoking to that initial projected surface. We plug that into the KK, the one should be identified with irrationality.